Department of Avionics at the Indian Institute of Space Science and Technology, Thiruvananthapuram. With a PhD in avionics from IIST and over 2 decades of academic and research experience, Dr. Prema has made significant contributions in the field of digital signal processing, multi-rate signal processing, and digital communication. She is a dedicated educator, having taught a wide range of subjects from analog circuits to modern signal processing, and continues to inspire future engineers and researchers through her expertise and passion for technology. Let's begin.
Thank you. So shall I start, sir? I'll share the screen and then start.
Yeah, please, ma'am, please.
Is my screen visible?
Yes, ma'am. Maybe it can be in full screen mode. Yeah.
Um, is it?
Yeah, slideshow.
Just, if you're not able to see properly, please let me know. I will share once again then. Is
I
it
think,
fine?
no, ma'am. I think this is a new file.
Okay. I think I will open it in just a minute. It'll-
Yeah, now it's visible. Maybe you can click on that slideshow, which is in the top.
This one?
Yeah, yes, ma'am.
I
Yeah,
think
now
fine,
it's
right?
now it's fine. Yeah, thank you.
Okay. Okay, sir. So I can go for 1 hour, isn't it, sir?
Yeah, even more than that.
Okay, I
No
have
issues, ma'am.
if you want, I can take it as 2 sessions also. So
Yeah.
just, okay, I'll go ahead then. So thank you all for this invitation. So today's talk is based on intelligent spectrum utilization in 5G and beyond 5G. So mainly, we know that in communication, without signal processing, it's incomplete. Okay, so my talk would over generally be with respect to communication and how signal processing can be used for this communication. Okay, so before I go into the talk, sir, anytime if my signal or anything is interrupted, please give me a call. Okay, because I'm not able to see any other screen here now.
Sure, ma'am.
Oh,
I will.
okay,
I will. Yeah.
okay, fine. So this is an overview. Fine. I'll directly go into the topic. So when we look at today's world, so there is an increase in number of wireless users, services, and there's a requirement for spectrum. But when you look into the spectrum, it's a fixed resource. It is not expandable. So the available spectrum has to be utilized efficiently. That's the most important thing here. So now when we look into how the spectrum is being utilized, we can see that certain portions of the spectrum are heavily utilized, certain portions of the spectrum are not underutilized. So we have to see that all the spectrum is utilized efficiently. So one of the techniques to utilize the spectrum efficiently is called as cognitive radio. So ideally what it does is it does the sensing and then goes for the bandwidth allocation. Now, when we look into, okay, why this 5G communication and beyond 5G communication has come. So as we all are aware, whoever is working in communication, we know now 6G, people are talking about 6G. But still, when we look into instead of going through all the generations, I have just picked up 5G and beyond 5G. So when we see this generations, the main quest is for data rates. So if you look at these things, you will see that we require high data rate. Next, we want efficient, energy efficient devices. Then latency has to be very less. Reliability, we say 99.9% we want it to be reliable, where we want high battery life. Now, if you look into this part, you have so much devices, that means 1 million devices per kilometer square, and we require a data rate of, let's say, 100 mbps and higher. Latency has to be reduced. Now, in between 5G and 6G, we have this beyond 5G. What is beyond 5G? It is just an extended version or an in between generation between 5 and 6G. Here, if you see, we want ultra low cost, we want 10 years on battery, more devices has to be connected, we want unlimited experience. These are the features which are being highlighted. We require more traffic, very less latency. Latency has to become lesser and lesser. Reliability, they said 99.9 percent reliability in 5G. Now we say that we want ultra reliability. Now, how to achieve all this? So to achieve all this, we require technology, so to address these issues. These are the problems. So for this only we require the technology. Now, so this is from one of the latest survey papers. We get these data. So if we look into the work, now we know that AI, everybody is talking about machine learning and artificial intelligence. Of course, they have taken up most of the areas, but here when we look into it, the one of the biggest challenges with respect to this is how we extract the features, how we generate the database. And now when we come into the communication part, how well we model the channel, then from that how we can detect the users. So mainly three main topics I thought that we will concentrate today mainly is, one is spectrum prediction, one is then automatic modulation and classification, and how CR in the sense cognitive radios can help in such scenarios. So now when we look into the underutilization, the birth of cognitive radio idea, or the intelligent receiver, we call that as intelligent receiver, also came with the this one of the, this is the key ideas for this. So when we look into the spectral utilization, see, we have two types of players. One is licensed users, another one is the unlicensed users. So when we talk about the licensed user, this person uses the spectrum only at times. That means the available spectrum becomes underutilized. And most of the time, the spectrum, some part of the spectrum remains idle. So FCC, or the Federal Communication Commission, came up with this idea telling that if the primary user is not using a particular spectrum, this can be allocated to a secondary user who can use the spectrum. But only one condition is, it should not create interference to the primary user or the licensed user. So from this came the cognitive radio. Now, what is this cognitive radio? So when we talk about cognitive radio, it's a radio or a system that senses the electromagnetic environment, and it can adjust dynamically or autonomously adjust its parameters and modify the system operation such that it can maximize the throughput, mitigate interference, facilitate interoperability, and access secondary market. Now, the word cognitive radio was coined by Joseph Mitola. Now, he came up with a lot of ideas. So, for example, when we say a spectrum is not utilized, we say that it is a spectrum gap, or a spectrum hole, or a white space. So, spatially, now we can see a lot of works coming, like spatial sensing, spectrum mapping, to if you have a geographical area, in that how many users are there, how much amount of spectrum is utilized, how much amount of spectrum is underutilized. So when we look into this, spatial and temporal unused parts of the radio spectrum can be considered as this white space. Now, they are also called as TV white space. So most of you will be aware that why it is called TV white space. So with the advent of digital communication, when the TV shifted from the analog to the digital communication, a large amount of bandwidth became free. So this spectrum was called as the TV white space. Okay, that's one more side to utilizing the spectrum efficiently. Now, who is a primary user? Who is a secondary user? So, primary user means he is the licensed user. He can also be called as the privileged user of a frequency band. And secondary user is an unlicensed user, and he is an opportunistic user. So whenever a primary user is not using a particular spectrum, this secondary user can use that particular frequency band. Now, how can this this so when we look into the spectrum, two important things. One is the primary user using a spectrum? Second thing is, if the primary user is not using the spectrum, just identifying a white space does not finish our job. After identifying a particular white space, this white space has to be allocated to a secondary user such that that person can use that spectrum efficiently. So this part was called as dynamic spectrum assignment. In literature, we will call this as spectrum monitoring, spectrum management. All this comes under the dynamic spectrum assignment or spectrum sharing, carrier allocation, all these then coexistence of different users, all this will come under this. So this is called DSA. Particularly in 2002, the FCC Spectrum Policy Task Force recommended the adoption of the spectrum sharing technologies, how the spectrum can be shared. So now here in this picture, we can see that with respect to frequency, power, and time, we can see identify the spectral holes. Okay, so these spectral holes has to be utilized efficiently. So this comes under the dynamic spectral assignment. Okay. Now, when we look into the cognitive radio as a whole, it is called as a cognitive cycle. Now, Simon Hawkins was the person who came up with this idea of a cognitive cycle. Now, what does this cognitive cycle say? We said that cognitive radio, when I say it's an intelligent radio who is aware of the radio environment. So, first part is the system sensing. That is, it has to get the RF stimuli. Okay, so and that means it has to become aware of the RF environment around it. Then it has to analyze that particular spectrum and tell, okay, a spectrum is vacant or it is utilized. So it has to take a decision, and based on the decision, it has to allocate a user. So all this put together forms the cognitive radio cycle. Okay, now moving on, these four important things, that is in itself, these four parts are four different. So sensing is one thing, management is one thing, mobility is how we exchange the frequency of operation among the users, then comes the sharing. Now in today's, if we take the 5G technology, one of the key 5G technologies will be device to device communication, vehicle to vehicle communication, vehicle to X communication, machine to machine communication. All these communications will take place. You can see a primary user and a secondary user part there. Now, when we look into the spectrum sharing part, see, they are open spectrum sharing. When we say secondary users have equal rights to access a spectrum whole. Now, in the licensed spectrum sharing also, we will see that generally when we take device to device or NOMA, non-orthogonal multiple access, all these things, we will see that the sharing between the different users will be in underlay system mode or overlay system mode. So what is this underlay and overlay system mode? Now, when secondary users are allowed to transmit simultaneously when the primary users are transmitting, then it is called underlay system. And if it is overlay, it is secondary users can transmit only when the primary users are not transmitting. That's why the coexistence and the sharing part comes here. Now, there are a lot of optimization that is required such that the bit rate and the power is optimized. So we know in overall, even though we say a lot of performance metrics, the two key performance metrics in communication when we take is the bandwidth and the power. How well we utilize the bandwidth, and we want the power to also be used efficiently. Now, when we look into this, the cognitive radio side part, we'll see two important features. One is the cognitive capability. Next one is the reconfigurability. Now, when we look into cognitive capability, it's like how well we sense the environment and capture the information. Okay. Then, based on the captured information, how well we reconfigure or how well we can intelligently adapt to the radio environment is the reconfigurable part. So these two modes when we take, so here we can now depending upon an environment, we have to study the environment, and based on how we have studied the environment, we have to do the decision making and the spectral allocation. So that's why here we can see the CR architecture. We'll have a reconfigurable platform, radio platform. So we can see that today software defined radios and many reconfigurable. The moment we bring in reconfigurability, it goes into the RF domain, also reconfigurable antennas, and in 6G we can see a lot of reconfigurable features have been getting introduced to dynamically align to the requirements of the users. So now when we look into this, here in particular, the radio environment is sensed. Based on that, so here you can see the feedback loop coming here, learned, then the decision is made, and based on that, the reconfigurable transmitter receiver is taking place. Okay, so this is the two features of cognitive. Why we call it intelligent is just because of these two features. One is the cognitive capability and the reconfigurability. Now, so what are the key objectives of this cognitive radio? Of course, we have to reduce the bit error rate, we have to minimize the power consumption, we have to minimize the interference, because there should not be any interference between the primary user and the secondary user. Throughput has to be maximized. When you're doing the sharing part, the quality of service should not be compromised. We have to maximize the spectrum efficiency and user quality of experience. So in short, all these bullets can be told in two terms: bandwidth efficient and power efficient. Okay. So moving further, we'll see that in the spectrum sensing, you will have the different types of sensings can be used. One is the single band, another one is the single band or narrow band, we can say, to detect the presence or absence of a signal. Next, we have the multi-band approach, where we have the primary users are sensed and assessed simultaneously. When I say multi-band, it can be a wide band where you have non-overlapping subbands, and based on that we do the sensing and then we get it. So one of the primary goals of a cognitive radio is the sensing part. Important primary job is sensing, and then based on sensing only the other things can take place. So we categorize them as serial sensing, parallel sensing, wideband sensing. So they are different methods can be used for performing this sensing. Next, when we move further, we will see that when we sense, after sensing the RF environment, we have this power spectrum estimator, weighted overlap spectrum averaging approach, filter bank approach, ML based approach. These are different approaches used to detect a user. So first we were telling we have to identify the spectral hole. So now sensing, when I say sensing, is the approach used to identify the spectral hole. So how we identify the spectral hole, we see, is by using any of these approaches. So there are a lot of literature we can see with respect to the spectrum sensing approaches: matched filter based, feature based approach. But one of the important things that the TV regulation standards tell about this is whatever approach you use has to be of low complexity, because the sensing time is very less. It should be very less. Based on that, it has to take the decision and then allocate the spectrum. Because when a secondary user is using a primary user's bandwidth, the moment the primary user requests the access, it has to immediately shut down and give the band to the primary user. So different approaches are there. So when we do a simple comparison between the different approaches, we will see that the energy reduction approach is the simplest approach. But the main challenge here is the performance is very poor in low SNR conditions. So based on that, there are a lot of works that can be carried out. These are the key four important works are which deal with the spectrum sensing part. Now, when we see this, we know that today learning or the AI and deep learning approaches have come, and many learning approaches can be used also in the CR learning process. So when we look into this, see, CR can make decisions concerning different variables has to be chosen for the CR learning. So if you look at this, see, we saw that there's a CR in the sense a cognitive radio, and from that the main part first that is going to take place is it's sensing, it's observing, it's learning. So when it learns from the previous observations and it makes a decision. So based on this, it can make a decision. So when you look into this part, the sensing, observing, learning part, what are the parameters required? First is power control, frequency band allocation, and time slot allocation. Then we have the adaptive modulation and coding. Then we have the frame size or symbol rate control, base station deployment is there, antenna selection parameters, handover, then admission control, congestion control. Various parameters can be learned by the CR, and based on that, it can make the decision on whether an available spectrum is free or it is utilized, and then it can do the spectrum reallocation. Now, moving on further, see, okay, just a break. Any questions with respect to cognitive radio? I will address this and then move to the second part. Any
Participants,
questions?
if you have any questions, you can unmute yourself, and even you can post it in the chat window.
Shall I continue, sir?
Yeah, please,
Okay,
please.
okay, okay, fine. Then I will go ahead. Just a minute, I think.
There is a question in the chat window.
What is the question, sir? I couldn't see.
Actually, Mr. Venkatachalam from PSC Tech is asking, can you say any real-time application of this cognitive?
Real-time application of?
Real-time application. Uh,
Yes, yes, for sure. Sir, is my is my screen visible? I'm unable to.
Maybe you can open your screen.
Is it visible now? Oh, sorry, sorry. I've gone to some other window. I think so. I think I have to share again. Sorry. Which is the screen you are able to see now?
We can see your entire screen. Maybe you can open that PDF.
I,
Next one. Yeah,
now
yeah.
what do you see?
Yeah. Now we are seeing your
Okay,
first
fine.
slide.
Okay. Yeah, I'll answer to that question. Sir, any real-time application in CR, isn't it? That was the question. So here, if you see this in European Union, many places they have deployed this cognitive radio where there are multiple users. Okay. So when there are multiple users, the licensed users as well as the okay, I think I will give an illustration for this and then I will go into that practical thing. See, for example, assume that there is a private road. So the private road belongs to the particular owner, but the owner might use it only twice a day. But there are other times when the road can be used by the other players. Okay, so they can use it. Only thing is, when the primary user is present, it should not use it. So what they do is they go for the spectrum sharing, where the other users can utilize the spectrum, the available spectrum. So they have this sensing part, and when the spectrum is free, the transmission can take place. So these are having a lot of applications. So actually IoTs, when we take the device to device communication or the vehicle to vehicle communication, all this part they have this primary user, the CR logic incorporated in it. Okay, I will move further and then I will take more questions. So when we look into the sensing part also, we have this cooperative spectrum sensing. See, when we are sensing with a single user, there is a chance that we might be wrong. So what they do is in cooperative sensing that we have multiple sensors, and all these multiple sensors are being given to a fusion center, and then the fusion center takes the decision. That means, so one particular band is being sensed by multiple users, and then based on that, fusion center is the decision making body or the spectrum monitoring body, and then the reallocation is being done. So here in cooperative spectrum sensing also, we have the centralized and the distributed, both types of spectrum sharing is there, where they are we use the cooperative model where we have a but of course they have some challenges because the overhead gets increased here. Okay, and then we use some and or some fuzzy logic to take the decision on how and or logics are being used by the different the input which has been received by the users, then the decision is being taken. Okay, so in cooperative spectrum sensing, when we see, let's say that we are having a p number of primary users and m number of secondary users. So all this information are given inside the fusion center, and depending upon the input, the fusion center takes the call whether a primary user is present or absent. It is based on the hypothesis. I'm not going into the internal details here. It's simple as this: the primary user is present or absent. That's the final decision it is going to take and declare it's a free space or not. Okay. Now, when we look into this, here again, the machine learning techniques are very useful in cooperative spectrum sensing. Particularly, we know that when we take the machine learning, we have the supervised learning, unsupervised learning, reinforced learning. All these types of learning comes into play, and based on that, we have different algorithms for each type. These can be utilized in the cooperative spectrum sensing also. So, ideally, you sense, you learn an environment and take decisions accordingly. Now, when we look into this part, see here again, this is the simple block or the system model for it. So you have different users, they all sense, they give this is the fusion center, what is inside a fusion center. So first you have the feature extraction, then training database, all this, then based on that we make a classification and then decide whether the spectrum is utilized or not. So when we do this classification, any type, see the feature extraction also, we have whatever we saw in the primary methods like the energy detector, covariance method, PCA methods can be used for the feature extraction here. Further moving on, see, okay, now up till now we saw with respect to the spectrum sensing part. Now next when we see, next is the spectrum prediction part. So we saw that one of the challenges we see with respect to the cognitive radio is that it has to have very low latency. That means we have to do the operation in a very fast rate. So depending upon the historical data or the observations, if I can predict the spectrum, then I can save time in sensing and the reallocation. So the next part is the spectrum prediction techniques. So when we look into the spectrum prediction techniques, there are a lot of, mostly here, these are all learning based techniques which I have told. So now when we look into the cognitive radio environment, we saw that for the cognitive radio cycle, we have 4 important parameters, that is spectrum sensing, spectrum decision, mobility, primary user mobility, and prediction. So all these things can be done using this general prediction algorithms. Okay. Now, when we see this, in today's world, when we look into the spectrum prediction techniques, we have to predict with respect to in the frequency domain, time domain, space domain. So what time, what frequency, and which location. That's why now we know in 6G localization, from 5G onwards, localization is another important feature that has been added into the communication. Now, when we look into this, further joint multiple domain is also there. So ultimately, when we look into a particular location, we have to, this problem or the frequency domain, if, for example, if I take the frequency domain prediction, it becomes a matrix completion problem. If I take it as a time domain problem, it becomes a linear predicted problem. Space-based, if you take, we take it with respect to graph-based methods. So even all these 3 put together, we'll see later that it will be a tensor completion problem. So ultimately, how we take this data and fit into a mathematical model, and from the mathematical model, what is the optimization which we require can be achieved. So further, we can use the ML or deep learning techniques here. All these approaches, all this type of prediction can be done with ML and DL based approaches as well as conventional approaches. So when we look into, whenever we say with respect to the learning approaches, the database and how we do the prediction is one side which we have to take care. Another one is the conventional techniques which we can use. Now, when we look into the spectrum prediction also, we take them into 3 types. Okay, mathematically, when I model it, it can be a 1D spectrum prediction, a 2D spectrum prediction, or a 3D spectrum prediction. Okay, different methods, literature we can see with respect to the predictions. Now, for example, I've taken the time prediction. Time prediction, when we say also, first, when I say it's a linear predictor, whether it's a AR model or a moving average model or a ARMA model or a ARIMA model, different models, auto regression, moving average, all these things, when we see which model we are going to take, and based on the model, what type of prediction we have to give to that particular model, and then what type of machine learning or deep learning models can be used for this prediction, we have to take care in this particular case. Now, moving on, for example, let's say I'm talking about the 2D problem. 2D problem, when I say the spectrum state, when two things I'm going to take, the power spectral density. So with respect to the power spectral density, frequency here I'm talking about. So we'll decide whether a particular signal is present or not. How it becomes a matrix completion problem? Let's see. See, for example, I'm taking only the frequency and the time here. So look at this. These are the historical observations. So historically, at particular time, but these frequency bands are occupied. The other frequency bands are empty. So if this is the case, then how we can complete this or predict the next time slot? So it becomes a simple matrix completion problem. How? Now, when I take this as a simple matrix, this becomes a sparse data, it becomes a low rank matrix, and there are different matrix completion algorithms. Using the matrix completion algorithms, I can complete this matrix and predict the data. Now, the beauty here, if you see, is see, there are normal data, there are also anomaly data, there are also missing data. In spite of all this, we will be able to predict the data here because of the condition of this matrix, where it is going to be a low rank matrix. Now, moving further, here we can see in 5G communication particularly, there is good correlation between the frequency and the time data. As a result, this matrix completion provides good prediction. The prediction here is very good, and then as a result, the spectrum can be utilized efficiently. Moving further, when we see these are okay, correlation in time and correlation in frequency is possible. So this is a simple algorithm which is generally used to in order to predict the or matrix. So it is ultimately, when you look into this actually gives us the complete idea of how the spectrum gets predicted and how the matrix completion helps in predicting the spectrum data and then utilizing. For example, when I say predicting, if I say that there are two, three bands are going to be vacant, then based on that, the spectrum allocation can be done here. Okay. So this is just the model. So I have the input plus noise is also there, or the incomplete or anomaly data is also there, can be in form of noise. So in spite of that, how we complete this matrix and then achieve it. Similarly, you have the joint spectral approaches also. Okay, joint, when I say recognizing the with respect to high correlation. See, for example, I will go into the model. Now, here again, if you look into this, see, this we have to complete a particular, I want to predict a particular spectrum. Based on that, I can train a network. Okay. And depending upon how well we have this deep learning approaches, we can predict. That can also be used. So predicting using the deep learning approaches have become, in recent days, have been very, research, highly researched topics. Similarly, in the 3D domain also, see, we saw only with respect to time and frequency. This can also be done with respect to the space as well. So when we take the space, it becomes a tensor here. So a matrix completion problem becomes a tensor completion problem here. So at what time, what frequency, which space. Here again, you can have missing data, you can have anomaly data. In spite of that, you will be able to complete your tensor and then predict what will happen. So you can also bring in mobility and other things into this picture. So when we look into this, the spectrum data are usually categorized with respect to location, time, frequency, signal strength. So in real world scenarios, when we take the spectrum data may be unavailable due to interference due to the acquisition problem or compression due to the sensing process. So in those cases as well, we will be able to predict, we should be able to predict the spectrum data. So for example, this one thing, say for example, you take the location, time and frequency. Here we have, this is the particular environment with which we want to model it. Here we can have primary user, secondary user, a base station is there, spectrum sensor is there, then geolocation database administrator. So what does this geolocation database administrator do? Based on the information it has, it can tell the complete spectrum map can be generated in a particular geographical area, how many users are there, how many spectrum, how the spectrum is utilized, and where the spectrums are free. If some secondary user is not having, is unable to transmit, you can check for areas where the spectrum is free or the white spaces are there, and you can start allocating it. Okay, so this is another. So here this particular model is being mainly being managed by the deep learning based approaches. Okay, so machine learning and deep learning extensively have been used for this prediction of the spectrum models. Okay, so these are some things, but we know, as we know, that the generation of data becomes a challenge and the channel models become a challenge. So different channel models and autoencoders can be used to generate this database, and based on this database, on top of it, this spectrum prediction can be run on, and the spectrum can be utilized. But of course, time, frequency, and space dimension information, when we are going to incorporate it becomes high computational complexity gets involved here. So generally, when we look into the significance of machine learning in cognitive radio, of course, we have to exploit experimentally the captured data, but it has to be trained properly with a variety of data. Particularly, it has to be robust in different radio environments, and it should be able to adapt to the new conditions and consistently yield good performance. Now, for example, when we look into this different architectures, algorithms, see, now if I don't know how well you're able to see here. Now you can see the cognitive radio network is in the center of it. Now, as we have seen, channel identification, spectrum management, then the resource management. Resource, when I say the spectrum and the power management comes into play, and the radio scene analysis. See, one point I want to measure here is when we say resource management, as we know, the technologies used for 5G. Actually, I'm not presenting those slides now. Particularly when we see the slides which we are having now will be, the technologies which we are having will be mainly device to device. And just a minute, I'm sorry for this. Just a minute. I'm sorry for that. I had a call. Okay. Are you all able to see my screen now?
Uh, Maybe you can project your file. The next one, yeah.
Are you able to see?
Yeah, yeah.
Okay. So when we look into the main parameter here, okay, resource management, the technologies used for 5G or beyond 5G is mainly device to device communication and NOMA. When we see, there are different users. For example, when I take the device to device communication, we know very well that we have a transmitter, a receiver, whether it is going through the base station, or how well we pair the different users and then allocate the spectrum. Then when I'm allocating the spectrum, again, how much power, all this has to be managed. So this part, you will have the power control and the resource allocation. So algorithm wise, when you see, you have to optimize the power and the resource here. Next part, when we see, let's take the NOMA. NOMA also, we have the non-orthogonal multiple access. When I say you have the near user, you have the far user. So near user, how much power should I allocate? Far user, how much how much power should I allocate? Similarly, when I take the two users, what is the information I'm going to give to the near user, what is the information for the far user, then the signal deduction techniques, how this successive interference and cancellation is going to take place between them, how the interference is getting mitigated, how the communication gets established between them. Everywhere the optimization is required. So next, when we look into this, see, you have the spectrum sensing part with the interference control as well. Again, channel, when I take the channel estimation takes place, as well as the channel prediction also has to take place. Next, when we look into this, whether how the spectrum allocation is being done. Of course, the spectrum auction is just the way with which you are going to declare it with respect to the licensed or the unlicensed users. So here, this particular slide only tells you what are the different machine learned algorithms that can be utilized in order to achieve this parameters here. For example, Q learning, KNN, SVN or random forest, as well as deep RL algorithms. In addition to this, we also have our conventional approaches, where using the conventional approaches, we can do the same thing like resource management, uh, similarly channel identification, spectrum management, etc., can be done with respect to this. So one part is using the learning based approach, another one is doing the conventional approaches. Again, when I go with the learning based approaches also, only from the conventional idea we know that what features can be extracted, and from the features which we can get the better results here. Okay. So one of the challenges when we will see is the complexity with respect to the real-time mode, convergence of this algorithm. If you go with learning-based algorithm, the data size, then another one is the generation of database. Then one important area which is very much still to be research, if you see, is the detection of malicious users. See, here we are only talking about a primary user and a secondary user. Any malicious user can act like a primary user and deny the secondary user any opportunity to do communication. So detection of malicious users and malicious attack is another one part. Of course, now when we look into the way with which the progression NOMA, RSMA are taking place, rate split multiple access, the extension of the NOMA based techniques takes care of all this malicious user and how the secrecy rate and other things can be used. Moreover, these algorithms have to be robust and scalable. Scalable in the sense, any environment they should be able to work upon. Now, moving further, when we see one another, so the first part we saw with respect to the sensing, second we saw with respect to the prediction, next another one is the modulation deduction. See, now when we go into the reallocation, in some cases it might not require, but in some cases we require that the modulation be identified, that is adaptive, automatic modulation and classification. Of course, we have adaptive modulation coding also. They both are based on the SANR and the bit rate for which the sharing can take place. So one of the major tasks of the intelligent receivers in cognitive radio communication, which we will see, is the intermediate step between the signal deduction and the demodulation. Now, when we look into the application, see, first we are getting, first part, we are deducting the user. Second part, what modulation it is having. Then based on that, we will know what modulation, when I am going to allocate a spectrum to another secondary user, what modulation it has to use. All these things can be taken care of by using this approach. So now next, they find application in many cases. For example, if the channel condition, based on the channel condition, we have to apply a modulation also. That can also be done based on this modulation reduction approach. Now, why this AMC is required in cognitive radio? If we ask a question here, the signal analysis and processing can be carried out only when the modulation of the signal is recognized. So essentially, for identifying the source of the received signal, then why we are telling with respect to the SDRs are based on this information, it can reconfigure and then transmit the other information whichever it is required based on the modulation type. Now, general, simple conventional techniques. Of course, we have deep learning and machine learning based techniques for AMC. I will concentrate mainly on the conventional techniques which can generally be used for identifying the modulation and classification. One of the approaches when we look into it is the likelihood based approaches. So based on the probability density function of the received signal, we can make a decision on what type of modulation it can be. So generally the Bayesian sense can be used here. Now, when we look into the features which can be extracted, for example, we can be signal spectral features, higher order statistics. Generally, in conventional approaches, higher order statistics are used, and that too in particular cumulant based approach or autocorrelation functions in cyclostationary based approaches, we use the autocorrelation function in order to identify the modulation scheme. But one important thing which we have to keep in mind is they all have to be of low complexity if they have to be used in real-time applications. Now, for example, if you take a likelihood-based approach, computational complexity is high. We need to compute the multidimensional conditional PDFs of the unknown parameters. Next, perfect channel state information has to be known. Now, if you take the feature-based approaches, it is low complexity, needs to low complexity calculations needed to extract this features, and it is generally favorable for real-time applications, but they will highly depend upon the database which we have. Now, if you take the feature based, challenges will be two or more features are required to achieve better accuracy. So, combining the different features and then classifying increases the complexity. At least one or two stages has to be computationally complex when we go for the feature. Particularly when we are going for this feature based deduction approaches, we should be very careful what feature I am going to choose, and based on that what is the training we will do, and based on that how we are going to classify this. Next is when we go into the deduction methods, so automatic modulation classification with respect to the learning based or other approaches, we can use the CNN or the cyclic feature, likelihood ratio, probability density function. These are the fundamental methods which we can use for the modulation classification. Now, when we look into the deep learning based approach, deep learning today we can see that they can perform well. This approaches can perform well in the higher SNR, but when it comes to the lower SNRs, they fail because of the database or the modeling of the channel conditions become difficult. So, particularly when we look into the traditional approaches, extracting. So this is like a extracting the signal features using the higher order cumulants, spectrograms, or cyclostationary features of the received signal. We can make the classification based on the SVM, decision trees, or KNN. Then also the another way is with the deep learning models, where it can learn the relevant features directly from the raw data and then do the classification. But of course, they will need complex feature engineering in order to incorporate such features. Now, to conclude with respect to this, so we, in general, we saw that CR can act as an intelligent radio, and then we saw that the first part is sensing, then we saw with cooperative spectrum sensing, then we saw with respect to the prediction, and then we saw how this modulations can be used. Now, in general, when we just to conclude this, we can see that some bands are significantly underutilized, but cost of dynamically leasing the spectrum is expected to be much lower than purchasing a licensed spectrum, isn't it? So when you have to go for a new spectrum, it's difficult, but the available spectrum has to be utilized efficiently. We require technology. Also, we have to allow expansion of spectrum at a much lower cost, in the sense with good algorithms. So to satisfy the spectrum demands of different users, intelligent systems, technologies are required. Now, when we look into the dynamic and opportunistic use allowed by the FCC, spectrums are required to cope with the different demands. See, we move from one generation to other generation. As somebody said that we have a lot of technology, but where is the infrastructure to use this technology? So to say in short, I can have a Ferrari car, but if I don't have a road to ride that, then it doesn't become meaningful. So same way, it all has to go hand in hand, that the dynamic and the opportunistic use of spectrum plus the technology have to be adaptable. So again, more adaptability needed to mitigate interference between the different users. And then when we look into this, the combination, particularly with respect to the power control, selecting the right frequency, the relaying, then heterogeneous hit nets are important, heterogeneous network architecture, space division, then localized intelligence are all to be certain things which can be innovated. Okay, so with this I conclude. I'm open for questions.
Yeah, it was very insightful presentation, ma'am. Thanks for your presentation and accepting our invitation. So, participants, if you have any questions, maybe you can unmute yourself or you can post it in the chat window.
Thank you, sir. Please feel free to ask questions. What I know, I can share.
Ma'am, I have two questions. Uh, Maybe before that, there is a question in the chat window. What are the
Okay.
features mainly considered for 5G spectrum utilization?
So when we see the 5G spectrum utilization, see 5G, when we say we are moving on to the higher frequencies. So when we move into the higher frequencies, again, why we are moving on to higher frequencies? We want to accommodate more demand from the users. When we accommodate more demand